like go for the capping. Okay, so I also discuss, like, I should just go through about the California crisis, where LMPs were very unpredictable, and after that, I think the US market, they decided to have a cap on the LMPs. So just a second. Kush, is it started recording as well? Okay, fine. So I will share my screen with you. Okay, and let's say Microsoft OneNote. So good morning, everyone. Okay. In previous classes, we basically studied about the network pricing, right? And if we are going into the market, uh, everything has to be basically like whatever we are doing. So all the services has to be charged. So you discussed that, in the network pricing, which was like, taken by Professor Bhakar. He discussed that like different pricings will be basically adopted for an distribution network as well as for transmission network, and there are different philosophies behind that. So he discussed about those. Kush, can you open the chat? That's it. Yeah, thank you. So apart from that, there is one more thing which needs to be priced, which is losses, network losses. Earlier, like, so we assumed that losses are neglected in transmission network, but not entirely. They are basically post facto calculation we do, and we also have certain basically pricing for those. And if it is, like, market based pricing, LMPs are used for settlement, then network losses are implicit part of those. Okay, like in ACOPF, the LMPs will give you the prices of losses as well. And I think with a particular example, have seen that the prices are different from DCOPF to ACOPF, even though there was no congestion. So that is because of the network losses. So we can say that whatever is the difference is the prices for losses. Okay, but in distribution network, it is very difficult to solve ACOPF, and it is not advised as well. So there are some different methods has been adopted for the loss allocation. Okay, that how we can allocate the losses. So there are some losses which are happening, and these needs to be allocated to the participants. Now let's consider a particular example. Let's say there is a line, transmission line or a distribution line. You can consider whatever it is, right? And some transactions are happening to this particular line, which is, let's say, P1, and another transaction is P2. So if we assume that voltage magnitudes are equals to 1, then power V, what is P? So it is like voltage into current. If voltage is not there, we can say these powers also represents current. So this, and I'm not considering for the time being the reactive power, only active power I'm considering. So in that case, the P is equivalent to current. So I can say that the losses basically are I square R. This is what we know, like, so if the resistance of this line is R, then I can say that I will be equivalent to P1. So the total current in this particular line will be P1 plus P2 square R. Okay, so this is very basic. Then if we bifurcate this one, it is P1 square and then P2 square plus 2 P1, P2 and R. So by looking at this, we can say that this P1 square R is basically should be allocated to the first player, or like first transaction. So like, this should be allocated to the transaction 1. Then plus we have P2 square R. This should be allocated to the whatever the transaction 2 is happening, which is of P2 amount. Then we have this two P1, P2, and R. This has to be, it has both the components P1 and P2, so it should be allocated to both transaction 1 and transaction 2. So this should be allocated both transaction 1 and transaction 2. Now there are different methods available in the literature and adopted by the system operator. We will just talk about like one of the emerging technology, and like one of the technique by like we want to use it. So that is so I will move the entire flow of this lecture to the game theory application, like how we can use game theory for the different settlement process. So like if you look at this particular part here, so this is 2p1 p2r. So how we can allocate this? Okay, so we assume that, let's consider that 2p1 p2 r is equals to, let's say, some beta 1 p1 p2 r plus beta 2 p1 p2 r. That some proportionate we will talk about, and whatever is this 2 p1 p2 r will be allocated to so this will be this entire term will be allocated to the transaction 1. Okay, so whatever is the beta 1 coefficient, based upon that we will allocate to the transaction 1, and this will be allocated to the transaction 2. So this is how we can allocate it. So by solving it, we get a condition that this should be beta 1 plus beta 2. Now the question is, what should be the values of beta 1 and beta 2? Okay. Am I audible? Perfect. Thank you. So there are different philosophies by which we can allocate them. So first is proportionate allocation. So in this they have a condition. So like I will name it equation number 1. Okay, and in proportionate allocation, we are assuming that okay, the power flows or the losses will be proportionate to the power, whatever is the power flow. So I can say that P1 upon P2 will be equals to beta 1 upon beta 2. So this is my equation number 2. And if I solve these equations, what will be the value of beta 1? Like if you, let's say I want to solve it, what will be the value of beta 1 and beta 2 in terms of P1 and P2? So these are the two equations. Okay, and there are two variable beta 1 and beta 2, and if I want to solve it, what value will I get out of it? So it is like if I put the values, 2 equals to uh, P1 upon P2 beta 2 plus beta 2, and here the beta 2 will be equals to 2 divided by P2 and P1 plus P2. I can say that, right? Similarly, I can obtain the value of beta 1 as well, which is twice of P1 upon P1 plus P2. So this is one allocation that okay, we are going to use these factors, and once the beta 1 and beta 2 are known, so this is using these two formulas, we can obtain the beta 1 and beta 2, and I can allocate, let's say, the first player will be the P1 square R plus beta 1, which is twice of P1 divided by P1 plus P2, and then P1 P2R. So this will be the allocation to the first player, and similarly we can calculate the allocation to the second player, which is P2R plus, let's say, 2 P2 by P1 plus P2, and then it is P1 P2R. So this is if you look at this term, we were able to allocate to the transaction 1 and transaction 2. So this is how we can allocate it. Now if I ask you, so this is one way of doing it. Another way of doing it is that basically the assumption is, or the philosophy is, and the second type of allocation, that the losses are not proportionate to the actual power flows, and they are basically proportionate to the square of power flows, and which is also valid. So by which by assuming this, we have come up with the quadratic allocation. Okay, I'll make it full screen. Draw eraser. Quadratic allocation, and here what I assume that the beta 1 and beta 2 are not proportionate to p1 p2, and they are basically proportional to p1 square and p2 square. So I will assume that this is my condition. So this is the third condition, and the very fundamental condition is beta 1 plus beta 2 should be equals to 2. And if I in the similar fashion, if I try to solve it, I will get beta 1 equals to twice of, instead of p1 it will be p1 square divided by p1 square plus p2 square plus, and then this is beta 1, and then beta 2 is basically twice of p2 square divided by p1 square plus p2 square. Okay, then there is another method or another approach which is called basically that the losses are not proportionate to the power flows, and they are also not proportionate to the square of the power flows. So they assumed that losses are basically geometrically proportionate, and they are non-linear in the nature, so by which we have come up with a method, geometric allocation. So geometric allocation. Okay, so we are basically allocating the transactions or losses to the different transactions happening in a particular line, and the very fundamental condition is basically beta I minus log of pi equals to, so it is beta 1 and then beta 2 minus log of p2. So this is what is the condition, and with the like beta 1 and beta 2 are constant, so if we use these simple bit simplification and try to solve it, it comes equals to 1 plus 1 by 2 log of p1 upon p2. Okay, similarly the beta 2 will also come equals to 1 plus 1 by 2 log of p1 and p2, and the one condition here is that this p1 by p2, because it is in the log, should be less than 100. The ratio p1 by p2 ratio should be less than and more than 0.0. Okay, so this is formulation which have to follow, and in generalized way we can write down like the if the beta 1 will be equals to 1 plus, so here we have taken the base 10, so if we change that base, it is 1 by r, and then basically it is log of p1 upon p2, and similarly the beta 2 will be 1 plus 1 by r and log of p1 upon p2, if the ratio is basically 10 to power minus r and then 10 to power r. So these are the two formulas which we obtained. Now the question comes that we have discussed three different formulas, and how we will, like, which one to use, like how we will decide that which one is better. Okay, so that is the question mark. So if I give you one particular example, let's say, so we have, let's assume that if I consider an example, let's say there's a line, and then P1 is equals to 10 per unit, and P2 is equals to 1 per unit. Okay, and let's assume the resistance is basically 1 for this particular line. So if I assume that R equals to 1 per unit, so this is P1 and this is P2, direction of P2. What will be the total losses? We discussed that it will be P1 square plus, sorry, P1 plus P2 whole square into R. So that will be 10 plus 1, 11 square into R. That will be 121 per unit. So this is the total losses which we are basically obtaining by solving it. Now we have discussed three methods. So if you look at the three methods, let's say the first one is proportionate allocation. So I am just writing it in very short, PA. So I can calculate the beta 1. Beta 1 was twice of P1 upon P1 plus P2, and that is 2 into 10 divided by 11, which is I think 2 by 11 is how much? Anybody who's who can solve these values for me? It is 2 into P2 was 1 divided by 11. So 2 by 11, and then 20 by 11. So it is 1.82, and then it is 0.18, let's say. Okay, so these are the values of P1 and P2, and if I use these values of P1 and P2, I can allocate, like phi1 to the P1 transaction, which was P1 square R plus beta 1 P1 P2 R. Here R was basically 1, so we can use P1 square, which is 100, plus beta 1 is 1.1, 1.82 into 10 into 1 into 1. So this will be equals to 118.18. Okay, so that is the allocation to phi 1 P1. Similarly, if I allocate like phi 2 P2, this will be P2 square R plus beta 2 P1 P2 R, and beta, this will be 1 because P2 was 1 and R is 1, so this is 1, plus beta 2 is basically 0.18 into 10 into 1 into 1. So that will be equals to 1 plus this 1.81, so it is 2.82 per unit. Okay, so these are the phi 2 P2 allocation. If you look at the allocation, it says that out of 121 total losses, 100, roughly around 118 should be allocated to the transaction 1, and roughly around 3 per unit should be allocated to the transaction 2. And it goes with the same thing that, okay, P1 is utilizing more the network, so it is creating more losses in the system. And if the losses are more in the system, then the allocation should be more. So that is also fine, that okay, P1 was 10 per unit, so it is basically having a losses of 118, which is very high as compared to the second allocation. If I again further go with the second method, which was quadratic allocation. Okay, in quadratic allocation, we obtained that beta 1 was 2 p1 square upon p1 square plus p2 square. So 2 into p1 square should be 100 divided by 100 plus 1. Okay. So what will be the values? And then b2 will be twice into p2 square, which is 1 upon 100 plus 1. So what will be these values? So this is 1.98 and this value is 0.02, roughly around. Okay. Now if I use the same method, that phi1 p1, so which is the, like, I'm using this notation for the allocation to the transaction p1, that will be again same p1 square r plus beta 1 p1 p2 r. And if I put these values p1 square r plus beta 1 p2 p2, this will come 119.80. And similarly the phi 2 p2 will come roughly around 1.20 per units. Okay, and the total is same, 128. If you look at both the allocations, in the first one, that P1 was getting roughly around 118 allocation, and then if we look at the second player, the allocation was 2.82. But if we use the different method, the allocation is basically very much different, and it is basically penalize the player or the transaction who's more as compared to the lower transaction. Okay, because if you see the lower transaction is roughly half, and the same amount has been compensated to the transaction number 1. So it's instead of 2.82, it is 1.2 only, which is, like, I think less than half, and whatever is the difference has been basically given to the transaction 1. So the question is, let's say these transactions are happening for some player 1 and player 2. Players can be like, like transaction between generation and load, or it can be like simply to the loads as well. It depends, like, how we are going to allocate the losses. Okay. So far we are not going into the discussion whether the losses should be allocated to generators only or to the loads only. We are assuming that there are some transactions happening, and those transactions are obviously between a generator and load. So we are like allocating those losses to those particular transaction between generator and load. Then once it is allocated to the transactions based upon like whatever is the agreement between the generation and load, they can decide that, okay, how we are going to allocate those. Either the entire, the allocation or the losses will be uh, allocated to the loads, or you can simply say that loads, the power flows are not only because of the loads, they are also because of the generator. So you can split them into 50-50 ratio, that 50% should go to the generator and 50% should go to the load. Okay, so that depends, like country practice and how the system operator is basically, or what are the regulations. So based upon that, we can do like allocate the uh, losses. Okay, but so far we have to identify that, okay, uh, which transaction is utilizing network more, and what should be the allocation to each transaction. Okay, now let's talk about the third one. Okay, so I will just simply write like geometric allocation. Okay, GA. And in this one, basically the beta 1 was 1 plus, I think, 1 by 2 log of P1 by P2. And if you solve it, it will come roughly around 1.5. And then beta 2 will come around 0.5. Okay. And if we allocate with the same formula, P1, we will get roughly around 115 per unit losses, and then allocation to the second player or the second transaction is roughly around 5 per unit. So the total is 121. Is this clear? If you have any doubts so far, so we have basically gone at three different methods. All of them are giving different allocation. So if I look at the, the transaction which has lesser amount, so like if I just look at the P2 point of view, P2 will try to go with the second method, okay, quadratic allocation, because it has very less allocation. Okay, so if I just simply like a proportionate allocation, and then we had a quadratic allocation, then we have a geometric allocation. And if I like what is the phi 1 and what is the phi 2, if I talk about phi 2 for geometric allocation is roughly around 5, and this is 105, and earlier it was 1.2, and then it is 119.8, and then 118.18, so it will be roughly around 2.82 per unit. So these were the allocations. Okay, so if I look at player 2 point of view, like how the player 2, he would suggest that okay, quadratic allocation should be adopted because I'm getting very less number of loss allocated to me. If I look at the player 2 point of view, he will say that okay, you should adopt the geometric allocation because that is the uh, very less allocation. So we have different methods. Okay, so far we have like different methods are there, and they results in different allocation. Okay, now the question is which method should be adopted. Those one is favoring one player, another is favoring another player. So let's talk about one more thing is, which is like then we have certain basically uh, type of modeling of the network losses, which is game theory based. Okay, so if we apply the game theory allocation. Okay, so first of all, first question is what is a game? Anyone, please. How will you define a game, first of all? So, applying game theory, we have to understand that what is a game and can we apply whatever is the principles of a game to our allocation problem, which is in power system. So, can you provide me like, what is a game, first of all? Multiple players try to win. So, yes, game is basically between two players at least. Okay, so two or more players. Okay, with set rules followed by each. That is also good. That certain rules be there. So two players, uh, some conditions. Yes. So objective. So certain objective will be there. Objective can be different, can be same. So let's say uh, if different objectives of players, we call it, and if it is like everyone is trying to achieve the same objective, So there can be two conditions that, okay, like you must have, if like me as already gone through those stages, so maybe I have I have not played these games, in COVID time there was many people playing PUBG. It was reported in the news as well, the students are playing PUBG game. And when I looked upon it, just for out of curiosity, it is not one to one game. It was basically like different kind of game. So there were teams, teams of maybe 3 people, 4 people, or 5 people. So those are the teams, and objective of team is same. So a team is basically having the same objective, and then those they were basically fighting with, I think, other teams. So we can say the different teams had different objectives, and everybody wants to win the game. So based upon objectives, and what will happen, suppose one team or one player, if one wins, another will lose, definitely, right? So it is basically one is getting some money if is playing the game, other must be losing the money. So once one player's objective is basically coming from the another players of loss. So in that case, if the different objectives are there, that kind of game is called non cooperative game. That players are non cooperative with each other. They are just looking at their own objective function, and they will not see whether other player is getting a loss, or if they are getting more. It doesn't matter. Their objective should be maximum, irrespective of what others are doing, what others are getting out of the game. It is not their objective. Okay, so multiple so the example which I gave, the example, there it was basically the same objective. Like everyone wants to, I think, defeat others, and whoever is the last standing, that party will win. But in real life, we can have multiple objectives, and they may be contradictory, contradict to each other. They may not, doesn't matter. So let's say, if I am trying to achieve certain objective, it may reduce the objective of the other players, or it may not, doesn't matter. But if I'm not cooperating with the others, and I'm not making a group with others to achieve my objective, I'm just looking at my objective, that okay, I don't care what others are doing. If they are in the loss or profit, I don't care. I will just look at my objectives only. Those kind of game settings are called non-cooperative game. Sometimes the different players works together, and they try to obtain a same objective, or you can common objective. So we sometimes the same objective. So it's basically we can say it's a society, and society is trying to attain a particular objective. So this is sometimes called social objective as well. That we are trying to minimize or maximize certain social objective, and this kind of game is basically defined as a cooperative game. Okay, so here can we use the same philosophy to our uh, basically problems. If I look at the non-cooperative one, okay, so the solution of non-cooperative game was given by John Nash, and on his name, it is called Nash equilibrium. Okay, So what they do is they try to like one player has certain strategy, another will have some different strategy, and one player will play its strategy to optimize its own objective. So player one will try to optimize its own objective, and then player two will also try to optimize its own objective. So the player two will have certain different basically strategy, and if the payoffs are basically contradictory, um, the equilibrium point will be the solution of the game, that nobody wants to move away from the optimal point, that is called equilibrium point. So that is non-cooperative game. Then we have a cooperative game structure, and the solutions are basically given by Lloyd Shapley. Okay, and that is basically called Shapley value. Okay, so apart from that, there are multiple other ways of as well, but just for the time being, let's nucleus can also be calculated, that we can calculate the as nucleus of the entire problem. So that is, there are different ways, core of a particular game, so different ways of doing it, but for the time being we will look at certain formulation. So let's say a non-cooperative game is basically solved with the help of the Nash equilibrium. Cooperative game is can be solved with the help of Shapley value. So question is, can we use so which method should we use? Whether non-cooperative can be non-cooperative game can be applied to the loss allocation problem, or we should apply cooperative game to the loss allocation problem. So if you look at let's say this is a line. Some P1 transaction is happening here, some P2 transaction is happening here, and let's say some Pn number of transactions are happening here. So if only P1 is there, okay, the loss will be P1 square R. If two transactions are happening, then it will be P1 plus P2 square R. And let's say all, let's say n number of players are there, then it will be P1 plus P2 plus Pn square R. So can we model our problem in this fashion? Okay. So if you look at this particular problem, losses are happening because of all the transactions. It's not because of only one transaction. And if I remove one player, the losses will also change. So actually, we can model this entire problem as a cooperative game, where we assume that all the players are basically working together. So like all players, and those are basically transactions for us in this particular problem. They are basically working together, and the objective is to produce losses, and they are basically producing losses. Okay, so this is basically our objective. Now if we assume that it's a cooperative game, everyone is working together and the objective is to create certain losses. In that case, we can apply Shapley value to this particular problem. We will discuss like how we can apply such particular. So it's basically we can say it is a cooperative game. If I look at the non-cooperative game, NCG, this particular problem can also be modeled as a non-cooperative game. Okay, so like in power system, we have different problems, and you have to see and you have to apply your own concept, how we can basically like which kind of very fundamental game type we can apply, and then look for the solutions, like how we can solve it. So each problem will have each distinct features, and we have to incorporate those. So if I look at the non-cooperative game, the same example, any player basically will try to get less number of losses. Like if you see, we had a table here that player 2 will say that okay, this should be my this method should be adopted. Player 1 will say that this method should be adopted. So everyone is basically trying to get less losses allocated to those, and that is I think very human nature. Okay, and that is also a rational behavior. So if I try to model this particular approach, what I can do is, let's say I'm writing it and generalize, like for any transaction I. Okay, so we are looking for the I transaction. It will try to minimize whatever is the beta I, pi, pj. That is the allocation, right? So this is the allocation to any player, and r is basically constant value, so I can place r as well. So this is the allocation. Okay, so if you look at the allocation part, in the very beginning we discussed that what will be the allocation to any player I. It will be basically this thing. So like for any player I, if I look at, the allocation will be this is self term, and there will be another term which is coming from the cross term. So this will be the total allocation, like if I add both of these. So this is called like self terms, and this term is called cross term. Okay, so each player will get a part of self term and then some part of cross term as well. Okay, so this self part is understood, it is common, and everyone is okay with it, that okay, yes, this much allocation is because of me, I can clearly see it. But they will focus on beta, that okay, if this beta is very less, then I will get less allocation in the common part in the losses. Okay, so if you look at this particular thing, we can define our objective for the non-cooperative game. And the objective is basically for Nash equilibrium we have to define a particular. So for this is like minimization of, and the objective is, the variables are beta I, and then I will try to minimize it, and the condition was what? Beta I plus beta j are equals to 2. This is the condition. Okay, similarly, the player 2 will also have the same condition, and if we so far we have learned in economic load dispatch that if conditions are there, we can solve it with the Lagrangian function. So Lagrangian function 1 will be beta 1. Let's say in terms of I and j, it is beta I, pi, pj r plus certain alpha or lambda basically. Lambda we are basically regularly using for the LMP, so I will not use lambda here, and I will assume that alpha is the variable here, the dual variable of this particular condition, which is beta 1 plus beta 2 or beta I plus beta j equals to 2, and I will put it here, and that is basically beta I plus beta j minus 2. Uh, the second player will also have the similar objective. He will try to minimize beta j, pi, and pj r plus alpha, and the conditions are the same for him as well. So these are the set of conditions. Okay, minus 2. So if we try to solve these basically two functions iteratively, like one is having certain action, then another is different action, and if we try to solve, uh, you will get certain value which is like beta I will be equals to beta j, and that will be equals to 1. So this is the outcome of the Nash equilibrium solution. So the Nash equilibrium will be at, so if you solve these things, will be at this particular point when both the beta I and beta j and both are equals to 1. So this satisfy our condition that the summation of both should be equals to 2. So yes, we can model at least this particular problem in both ways, cooperative game and non-cooperative game. Okay, in non-cooperative game, ith player is trying to minimize its own allocation, jth player is also trying to minimize its own allocation, and then they will basically both the objectives will be solved together, and at the end we will get this particular equilibrium point that beta I and beta j are equals to 1. If you have any doubt so far, please ask. Yes, Suman, like put earlier the question that like some conditions will be there, and the objectives can be like the players can be considered like they have some certain consensus uh, between them, so that is cooperative, and they can be considered as a rival, so that is non-cooperative. So the next way of solving is Shapley value. Okay, so Shapley value, I will just write down a formula. That Shapley value formula is basically given like this: summation over S, which is subset of N, and ith player is basically element of S. I will explain this particular formula in detail, and then set S minus 1, okay, and then a factorial of this, and then we have N minus S, and a factorial of this divided by N factorial, and then a value of S minus value of S minus I. So this is the formula for Shapley value. So if you see, there are different terms used for this particular formula. It is given by the Shapley in maybe I think 53, if I don't correct like remember it right. So let's not go into that. Just assume that okay, this is the formula. There are another one variation of as well for this particular formula, but yes, we can use this particular formula. So what are different things here? So this is phi I is basically the allocation to player I. Okay, that is understood. Then we have N. N is basically a grand collision or grand group, we can say. So it is basically COA collision. So small n is basically total number of players. So the grand collision will be basically a set or a group, we can say. Okay, so it's a Shipley value is cooperative game. So the players are cooperating with each other and forming a group, are basically collision. So the grand collision is basically like all the players are basically present. Okay, and that is called ground collision. Uh, S is nothing but a subset of N. So I can say that S is a subset of N. Okay. Then we have value function. So value function is basically objective or whatever is the social value, basically. Value of group, or I would say collision S. So this is the objective value or the social value of the group S. Now, how can I apply this particular formula to the loss allocation? So, in the loss allocation, we will see later on. First, I will just give a like what are the other conditions by which we can apply the uh, this particular Shapley-Wiley formula. So there is one condition as well to apply this particular one, and condition is basically we have a value associated with each and every player, that each player is responsible to basically provide a particular value in the group. So let's say if I am working together, and let's say we had a one example, right? 10 per unit power flow and 1 per unit power flow. So 10, if I assume only 10 per unit power flow, the losses was P1 square R, and R is assumed 1, so that will be the losses will be 100. So like just with from the example, if I say the value of first transaction was uh, P1 square R, so that is like if only player 1 is present in the system, I would say it is 100. And if I say value of second transaction only, so only second pair is present in the system, so the transaction was 1 per unit, and that value will be 1. So if I add these values, V1 plus value 2, this will be 101. Okay. So if they work individually, uh, the value of only first player will be 100 only, and value of second player is 1. Okay. And the total value is 101 only. But if they work together, like both the players work together, so both the 10 per unit transaction and 1 per unit transaction happen simultaneously. In that case, I can say that the value of 1 comma 2 will be, and that we already sold, right? Can you type those values? Like if both the players working together, what will be the value? And value in particular, like loss allocation problem is network losses. So what will be the losses if both the players are working together? Working together, we can say both the transactions are happening together same time. What will be the losses? Anyone who can tell me what will be the losses? There are more than 20 participants. I'm expecting one response at least. 101. If both are working together. So others, do you think that the if both player 10 per unit and 1 per unit transactions happen simultaneously in that particular line, which like that particular example, what will be the network losses? Just to inform you, 101 is not correct. That is basically when we add individual response. So like player 1 individual works, the losses will be P1 square R, and that is 100. And if player 2 individually works, it's a 1 per unit transaction. So P2 square R, and P2 is basically 1 only, so it is 1. So the losses will be 100 and plus 1. So the Shilpa 301, no, 301 is not also not the answer. So if you look at this particular problem here, initially I actually gave you the answer the very beginning. So and I also made one mistake, and you were not able to identify it. So I will go that there as well. So like this was the initial formulation we had, and then we basically yes, Suman. Now you are right. The total losses will be 120. So if both of them are working together, the power flows will be yes P1 square plus P2 square R, and that will be 121. Okay, and there is one more mistake which I made purposefully, that I have written here. If you see the, like, these are the beta 1 and these are the beta 2. If I use these coefficients, the allocation to the first pair is 115, and the allocation to basically the second pair will be 5. But this is not correct. If you use this particular formula, and you could have seen that the total sum was not equals to 121, which we had as a losses. So this is basically 6 value, 0.6. So this value will also be 6, and then it will be equals to basically 121. So I will just correct it, that this is not the case, it is 6. Okay. So I just wanted to see, like, if you are calculating everything with me or not. So that's why I made it like that. Now, yes, so we have converged that the total losses will be uh, P1 square, sorry, not P1 square, P1 plus P2 square. So that is P1 plus P2 square R, and that will be 121. The very first condition to apply Shapley value is basically the summation of individual players, or the value of individual player when only player I is present, that should be always more than and equals to the sorry, less than and equals to the value of entire players. So our capital N was grand collision when all the players are present. So the individual value, or if we add the individual values, it should be either less than or equals to, then only it is fair to apply the Shapley value. So here we can see that 101 is very much less than 121. So yes, we can apply the Shapley value. Now, the question is how we can apply the Shapley value. So I will consider one particular example. Let's say, okay, one more notation is needed, which is basically here we have defined. Yes, are the Shapley value and nucleus based base cost allocation in network pricing current trends in research, or there are any new methods for cost allocation other than this? So to be very honest, the Shapley value we are using for since a very long time, and but still it's basically how you look at the problem, and you can always come up with some new contribution from the research point of view. So it's not about like a trend. The scenario is always keep on changing. So like earlier we whenever these methods were adopted, they assumed that the generation and the loads have certain fixed value, and they do not have any uncertainty associated with them. But as we are going with, like very high share of renewable, uh, the renewable will affect the loss allocation. And the question is, you can still say that okay, it's basically losses are happening at the time of delivery, so it is happening in real time, and the allocation will be done after the power has been consumed or whatever time we are talking about. So we know exactly what will be the value of the generation, exact optimal value, and what will be the value of the loads. But the issue is, everybody wants to know what charges they are going to face if they are making a particular transaction. So they want those transactions are basically charges for losses as well, to know upfront a priori basically. So we can always basically come up with the methods those can handle uncertainty in them. So if some players are very much uncertain, they should face more contribution in the losses, because of them everything is uncertain. So it's again, it's my thoughts. You can always have build your own thoughts or build your own assumption, and based upon that assumption you can work on your own problem. So yes, you the loss allocation, it's a, you can say, very much saturated topic earlier, but from the implementation point of view, it has still have very much scope, because earlier, again, I just as I told you that everything was deterministic and the fix, but now it has been very much dynamic because of the uncertainties. And if you can handle the uncertainties with this, like you want to incorporate uncertainties in the loss allocation, yes, it's very much new. Okay, so yes, so we were talking about the condition, and I wanted to highlight one another collision. So we had considered a grand collision. I will consider a null collision as well. So it's a it is called, let's say, null collision, or you can say empty set. Okay, so there is nothing in the set. So if I give you certain values, can you obtain the basically Shipley value? Let's say the value of uh, null collision is 0. Nothing is there. Then let's say the value of first player is 3. Then the value of second player is 0. Then the value of third player is 1. Then let's say the value of 1 and 2 both are happening simultaneously, or both are working together. Then the value is again 3. And if value of 2 and 3, if I talk about, it is equals to 1. And if the value of 1 and 3 is equals to, let's say, 5, and then we will talk about the value of 1, 2 and 3, like when all the players are working together, then what is the value? So if 1, 2 and 3 are there, let's say the value is 5. So first of all, I look at the condition that summation of individual values should be less than equals to the value of grand collision. So if I implement this one, it is 301. 4 is less than 5. So yes, we can apply the Shapley value. Now if we again write it down, like the what was the, let's say, player 1 value, uh, it was basically summation over S set of n, and I was set of S. Okay, and then certain values are here, which was, I think, S minus 1 factorial. Okay, this inverted I is factorial. Okay, and then we had n minus S factorial divided by n factorial, and this is basically value of s minus value of s minus I. This thing is called marginal value as well, or marginal value of I to set S. So basically, what is how or why I'm calling it marginal value? Because like we are calculating the difference between two values. One value is basically a set S which has ith player in it, and if I remove that ith player, what is the value left in that particular set? So this is basically the difference is gives you the marginal value of ith player, that if ith player comes into a particular old set, it brings certain value or it increase the value, and that increment is called marginal value. Okay, and this is basically like the physical significance of this initial term is basically the probability of ith player to join set or 4 join set S. Okay, so this is probability. Now, how can we apply it? So first of all, if you look at the summation, it is summation over all the sets which are subset of n. So all of these sets are basically here we have defined, like how many subsets will be there. So the number of subsets sets will be equals to 2 raised to power n minus 1. So here we have considered 3 players. So 2 raised to power 3 is 8 minus 1 equals to 7 number of sets will be there. Okay, and if I remove if I say that it is 2 raised to power n, I can also say there will be at 8 number of sets. There can be 7 number of sets. So 7 is basically excluding null collision. So we are in excluding this 0 or where no one is present, and if we include the x and null collision, we can say there are 8 number of sets. So this is true for any n number of players. So we have 3 players, so you can see there are basically 8 different sets I have identified. Okay, so these are the all the combinations which are possible with the 3 players. Okay, so now I have to add these. Basically, to calculate the Shapley value for I have to satisfy these two conditions, that I have to make a summation over these two conditions. First of all, I have to look at the ith player. Ith player is basically, so I equals to 1. So where is player number 1 is present? So I can see player 1 is present here. Okay, so I is basically we have written I is element of S. So I am trying to identify the subset S where I is element. So this, and then second player is this, and the third one is this, and the fourth one is this. So I have to make a summation like that S for I will be equals to like set 1 when only player 1 is there, and then 1 and 2, and then 1 and 3, and then 1 2 and 3. So this is the summation which I am going to perform. Okay, so this satisfy this particular condition, that I should be the element of set S, and S should be the subset of n and equals to as well. So that's why we have considered this grand collision as well, that it is equals to. So let's put it. Phi 1 value will be equals to, first I will go with the particular set S. So it is basically okay, what this gives. So like this information is basically number of members. Okay, so for this is S, then what will be the S bar for these sets? So for this particular one it will be 1, for this particular it will be 2, for this particular one it will be 2, and then here we will have 3. Okay, so if I perform the summation, I will get something like this, that phi of 1 will be equals to so S bar, like in the mode, it is 1 minus 1 factorial, then n is 3 minus 1 factorial divided by 3 factorial, and here I will put value of S, so it is 1 and minus, when 1 is removed here, S minus I. So when 1 is removed, which means we are end up with the null collision. Okay, so this is 1. Then I will do the summation over the second set, which is 1 2. So for 1 2 it will be 2 minus 1 factorial and 3 minus 2 factorial divided by 3 factorial, and then value of 1 2 minus value of 1 is removed, so that is second. Similarly, I can calculate value of this factor as well, 3 minus 2, and then 3 factorial, and then value of 1 3 minus value of. If you have any doubts, you can put it in the chat box. You can raise your hand, we will discuss. And then for the last fourth set, it will be 3 minus 1 factorial, and then 3 minus 3 factorial divided by 3 factorial, and then value of 1 2 3 minus when 1 is removed, so that is value 2 3. Okay, so if I solve it, it is equals to so 1 minus 1 0 0 factorial is 1, 3 minus 1 is 2 factorial divided by 3 factorial, so it is 1 by 3, and value of 1 which we assumed roughly around, so 313155. So 3, so value of 1 is 3 and null collision it is 0. So this is first part, plus this will be, I think, 2 minus 1 1 1 factorial 1 is 3 minus 2 1, so it is 1 factorial divided by 3 factorial, that is 1 by 6, and value of 1 2 was 1 2 was 3, and value of 2 was 0, plus 1 by 6, value of 1 3, I don't remember it now, 1 3 is 5 and 3 is 1, so 1 3 is 5 and 1, and plus 1 by 3, and the overall value was 5 minus 2 3 2 3 was 1, 5 minus 1. And if we try to solve this particular things, we will get certain phi value. So this is phi 1 value will be equals to, I think, it's 1 by 3, so it's 2 by 6. So 6 plus 3 is 9, 9 plus 4 13, 13 plus 8. How much it is? 21, 21 by 6. So this value will be equals to 21 by 6. Okay. Similarly, you can obtain the phi 2 value and phi 3 value, and you can see that I'm assuming that for this particular problem, how to interpret Collisional rationality and individual rationality in terms of loss allocation in non cooperative and cooperative game. So this is what we already discussed, like they all the players are working together to the same basically objective, and we are assuming that everyone is rational. So the question is whether they are true to their actual information or not. So yes, I will go into that, whether like how much rational they are behaving in a collision. So individually it is fine that they are individual, so however they wants to behave, it's completely fine. But in a collision, how they are behaving, so we'll talk about that. Okay, now this is how like you can calculate the values. And if I was just created this particular numerical straight away, so what I can see is basically 2 has no improvement here, 2 has no improvement. So Shapley value for 2 will be equals to 0, or should come equals to 0. I request you to solve it. And if Shapley value of 2 equals to 0, I can easily calculate the Shapley value of the 3. And that will be basically just, let me use my calculator. It is 5 minus 21 divided by 6. So that will be 1.5, and then it is 21 by 6 is 3.5. So these will be the values. I'm like assuming that you will be able to solve this one. I will share this like notes with you in terms of PDF, so you can solve it. Now coming back to loss allocation. Okay, so we have two players, and those players are P1 and P2, and P1 had the value of 10 and P2 had the value of 1. Okay, so the value function is basically losses. So I can say the value of P1 and P2 is 121. This is what we have already calculated. The value of 1 we have calculated 100. Value of 2 we have calculated 1, and the value of null we have calculated 0. Okay, if I apply this like Shapley value, the allocation 5 1 will basically come equals to how much? It will be 1 by 2. Okay, so I again request you like go through it and solve it how we are getting it. So it is 1 by 2, and the value of 1 is 100 minus 0 plus 1 by 2, and value of 1 2 is 121 minus, if 1 is not present, 1. So that will be roughly around how much? Can you tell me? 50 plus 60, 110, right? So this will be equals to 110. Similarly, phi 2 P2 will be equals to 1 by 2. It will be equals to 1 minus 0 plus 1 by 2, and 121 minus 100, and that will be equals to 10. 10 or 11, I think. Huh? It should be equals to 11, right? So it is equals to 11. So total is 121, and this is the allocation. So if you like use Nash equilibrium or Shapley value, and rework everything, you will get beta 1 equals to 1, beta 2 equals to 1. So in Shapley value Nash equilibrium, we have defined that beta 1 will be equals to 1, beta 2 equals to 1, And for Shapley value as well, this will be the same. Beta 1 and beta 2 will be equals to 1. And if you, let's say, Shapley value, use Shapley value or this, or let's say if you solve for nucleus, nucleus, you will get the same outcome, that the beta 1 and beta 2 will be equals to, or should be equals to 1. And the location, as we already defined, like for Shapley one, it will be p1 square r plus beta 1 p1 p2 r, and that will be equals to 110, and phi 2 p2 will be equals to 10 if I put the values here. Okay. So all the methods, whether it is non-cooperative, which is we are solving with the help of the Nash equilibrium, or we are solving, let's say, cooperative game, which is by the Shapley value or the nucleus method, we are getting the same values of beta 1 and beta 2, and these are like the location is 110 and 10. Still, the question is, like, the very big question is, so far we have looked at the proportionate allocation, we have looked at the quadratic allocation, okay, and we have looked at the geometric allocation, and then we have looked at the game based allocation. Okay, game based allocation, they all are basically providing me the different results. And if I see from the player one point of view, game based allocations are much better, because they are only allocating it 110, and others are basically allocating more to the player one. And for player two, we have seen that I think quadratic allocation is better, because it was getting very less. So again, the question remains same. We have seen that earlier we had certain assumptions, like proportionate allocation or the quadratic allocation or the geometric allocation. So they should follow, different proportionate to these beta 1 and beta 2, and we have identified three methods and we were able to get some results. Then we moved that, okay, this entire problem is basically looks like a game, and generally, like, all the game theory based methods are considered to be fair. Okay, so whatever is the allocation will come out of the game theory based modeling will be fair. But how we know? So that this 110 and this allocation of 10, so these two allocation, whether it is good or bad, it's again a question mark. So for that, basically, we will look at one thing which is called aggregate invariancy. Okay, so how we can basically solve it? So the term is it is basically one of our paper as well. So we will look for the okay. So it is CY. Okay, aggregate invariancy. So how we can see that? So whatever the method we have discussed so far, they should work perfectly fine, or they should give me the same allocation, even if some modifications are there. So what I have done is, let's assume the same example. This P2 was 1 per unit, and let's say P1 is basically per unit, and then P12 is basically 5 per unit. So we still have the same transactions. One is basically 10 per unit by player 1, and player 2 is having the same transaction of 1 per unit. So the total losses are same, 121. And we basically assume that This player is smart and it split it that okay, I'm not having one transaction of 10 per unit, I'm having two transactions of 5 per unit. Okay, so let's name something else. Okay, so the losses will be basically P11 plus P12 plus P2 square R. Here if you look at the allocation will be P11 square R plus P12 square R plus P2 square R plus 2. There will be different close terms. So that is P11 P12 R plus 2 P12 or P12 P2 R plus 2 P2 P11 R. So this will be the total like if I expand this formula. Now here let me use a different color. Let's say I want to allocate the losses to the first player. So this term will be there. Then a component from this will be added to part, and then P11 is here in this particular box. So we will have a two terms. Okay. So can you solve what will be the beta 1, beta 2, or basically beta I and beta j for these three terms? So I'm again rewriting it. So let's say the phi 1, which is like for P1, P11 will be P11 square R plus some beta 11 when okay, how we do the notation. Let's say I'm making it C1 cross term 1, cross term 2, and cross term 3. So beta 11 from the C1 plus P11 P12R plus then some beta 11 will come from the cross term 3, and that will be P2 and P11R. So this will be the allocation, right, for the first player. Similarly, we can calculate or basically do the for the second player as well. So like if I just P12 player, it will be P12 square R plus beta 12 from the cross term 1 P11 P12R plus beta 12 is from the cross term 2 and P12 P2R, and then last for the transaction P2 third player, that will be P2 square R plus beta 2, and that is from closed term 2 P12 P2R plus beta 2 closed term 3 P2 P11R. So these are the allocation, and we can apply different methods here, which one is basically proportionate allocation, where beta I is basically twice of pi upon pi plus pj, and then we apply quadratic allocation, then we apply geometric allocation, and then we apply the game. And in game we have already solved it, that it will be the beta I will be equals to beta j, and that will be equals to 1. So this is already solved, that game theory will give you the same answer, that beta y or beta j for these closed terms should be equals to 1. But here we will get some different solution, like it is 2 pi square upon p1 square plus pi square upon pj square, and this was I think beta I equals to 1 plus 1 by 2 log of pi upon pj. So these are, different beta values. And if I put these values here, what will be the result basically? So let's say, first of all, let me talk about the proportionate allocation. Then I have certain cross terms. Okay. So first cross term was basically C1, and in this C1 I will get beta 11 C1 and then beta 12 C1. Okay. Then I have a second cross term which is beta, I think, okay. Second cross term was 1, 2 and 2, 3. Okay. So 1, 2 and 2, 3. I will go to that beta. Where is my cursor? 1, 2 C2 and beta 1, 2 and 2 C2. Then we have further third cross term which will have beta. What was the third one? Push beta 1, 1 C3 and beta 2 C3. Okay, so let's try to solve these values. So for proportionate allocation, this value will be 1, 1. Okay. Then if I solve it for, like 5 per unit, and so this is for 5 per unit and 5 per unit. This is for 5 per unit and B2 was 1 per unit and B11 was 5 per unit and B2 was 1 per unit. So if I solve it for those values, uh, I will get, I think, 5 by 3. So I have it with me, 5 by 3, then 1 by 3. Okay. Then we have another value is basically 5 by 3 and 1 by 3. If these are the values, uh, can we allocate the losses? So these are the values, like let's say P1, P2, P3. Can we get these losses here? Let's say I have empty space in between. Let's say I will try to calculate this here. So 5, 1 will be P11 is 5. R is 1, so I'm neglecting this. So P11 is 5. 5 square is how much? 25 plus beta 11 C1 is 1 into P11 is 5 into P12 is 5 plus beta 11 C3. Beta 11 C3 is 5 by 3 into P2 was 1 into P11 is 5, and that will come equals to, like, how much value? 50 plus 25 by 3. So 58 point. Thank you. So this is 58.33. If I calculate phi 2, so this is for P11 and this is for P12, and for P12 it is again 5 square, which is 25, plus P12 C1. P12 C1 is 1 into 5 into 5 plus, and P12 C2. P12 C2 is 5 by 3, and then we have P12. P12 is 5 into P2 is 5, 1. So that will also be the same value, 58.33. And if I add these values, because they are two different transactions, okay, but they have same values. That will come 116.67 roughly around. Okay. So similarly, I can calculate 534 player transaction 2, and that is P2 square is 1 plus B2 C2. So this is B2 C2 is 1 by 3, and then we have P12 is 5 into P2 is 1 plus B2 C3 is again 1 by 3, and then we have 1 into 5, so it is 5 plus 5, and it will come roughly around 4.33 to make it equals to 121. Okay, so what I'm doing is I'm looking at the loss allocation. If we have splitted the 10 per unit into two parts, so I can say that the actual load or the transaction 1 PT1 will be equals to the whatever is the so this will be equals to basically like 5 1 P1 will be equals to 5 1 P11. So this is like old nomenclature which we are using, and plus 5 2 P12. So this will be the allocation to the player number 1, and then we will have some allocation to the player number 2, which was like old allocation, that here it will be third player, so it is 5 3 P uh, P2. Okay, so by looking at this, I can say that the total allocation is here is 116.67, and it is 4.33. So how to interpret collisional rationality? So if you look at these two figures, so just remember it is 4.33 for player number 2, and 100 and remaining like 121 was the total, so 121 minus 4.33, so that is 116.67 to the player number 1. This is when everything is same. If you see, it is still 10 per unit and still 1 per unit. So but here we have splitted 10 per unit into two parts, so we are basically looking for the invariant nature if we disaggregate or aggregate certain players. So what was the initial allocation when we had this? If you see, for proportionate allocation, the second player allocation was 2.82 earlier, and if the player 1 is, and player 1's allocation was 118.18, but the player 1 is still 10 per unit, but like it's somehow playing with the its a big size and split it the 10 per unit into two transactions of 5 per unit each, and if we allocate the losses to 5 per unit first part and then 5 per unit of the second part, and if we add them up, the total loss allocation with the help of the proportionate allocation method is coming equals to 116.67 as compared to this 118.18. So by splitting virtually, like the big transaction can acquire less number of losses. So this basically indirectly penalize a smaller player or a smaller transaction, which is like which cannot like split further. Let's assume the like 1 per unit is the like minimum, and otherwise it will go to very minimum value, like everyone will split themselves to infinite number of transactions, to avoid or to basically attract less loss allocation. So like if player 1 disaggregate itself and split into 2, the player 2 will be allocated more losses. So instead of 2.82 in the genuine case, it will be allocated 4.33. So which is like you can say 1.5 times. Okay. But so I'm not going into like how much times, but yes, it is more as compared to the whatever is the previous allocation. Okay. Now the question comes, uh, will it happen to quadratic allocation as well? Okay. So if I use the same technique that okay, everything is basically splitted into two parts. So like the first 10 per unit is splitted into uh, two parts, 10 per unit, 5 per unit, 5 per unit, and second is still one. Then everything is same, but we are applying the quadratic allocation, and we are trying to use this particular formula, which is beta equals to 2 pi square upon pi square plus pj square. So we'll get some different beta factors. Okay. So if I look at the quadratic allocation, okay, the beta 1, beta 2 will be 1, 1 for this particular case. But after that, it is basically at 25 by 13. Okay. So it is 25 by 13, and then it is 1 by 13. Then this is again 25 by 13 and 1 by 13. So this is we will get, these will be the factors, and if I use these factors to allocate to the losses for both the transactions, I will get roughly around some values will be there. So I have those values here with me. So it is 119. So it is 119.23, and the player 2 will be getting 101.77. Similarly, if we use the geometric allocation, the factors will remain same, and this will be roughly around 1.35, and this will be 0.65, this will be 0.65 and 1.35, and the allocation will be different as compared to the previous case, and it will roughly be around 113.5. Earlier it was, if you remember, it was 115. Now it is 113.5, and the third player will get approximately 7.5. So instead of 6, it is getting 7.5. So everything is basically increased as compared to the actual values when no separation was there. Okay. So if I apply the game theory, whether it is Nash, Shapley, or Nucleus, the values will be 1 and 1. These will also be 1 and 1, and these will also be 1 and 1. And if you solve with these factors, the allocation will be 110 and 10, which is exactly same as the previous value. So by looking at this particular table and like solving it, the same question, it is still the same example. One transaction of 10, another transaction of 1 per unit, and we virtually splitted the 10 per unit into two parts, 5 per unit each, and we were trying to check whether these methods works without and they works efficiently and does not basically affects the final outcome. But yes, you can see this is basically changing its values. So earlier it was 118.18. So the player 1 is getting, this value has been reduced, and this value has been subsequently be increased. The next part was 119.80. So if you look at, the value is decreased, and this will be subsequently increased. Instead of 1.2, it is 1.77. This was 115, and then it is decreased, and subsequently it has been increased. Earlier as well, like, these are equal values basically. So no change in the game theory based allocation. So by looking at these results, we can comment that, out of different philosophies and approaches, uh, we should we should apply game theory based allocation for the losses to the particular transactions. Okay, so, like, the cross terms are well defined, and if you have some doubts, you can ask me. Yangya, I hope I'm able to answer your last question. Yes. So, what is a cross subsidy? So, cross subsidy is, two different, in what context we are using it. So, generally, like, cross subsidy means uh, taking out value from one participant and giving it to the somebody else. So, in terms of loss allocation, how the cross subsidy, what is the cross subsidy in terms of loss allocation? If I talk about, in general, it is like, we give subsidies to the farmers, and also we are reducing the prices, and just to get that money. So because it's a loss to the distribution company, that will be passed on to the usually industrial and commercial consumers. So that is cross subsidy in terms of tariff. But here, if we look at the problem, so far we have considered an example where we had a transaction in this particular direction, and another transaction was also in this particular direction. So I was assuming that there are two loads of P1 and P2, and I can assume that some generator was supplying this P1 plus P2. So this is very fundamental or basic example we can understand. Okay, so our we can sometimes also call it, instead of generator, we are talking about, this is like, let's say if it is distribution network, we can call it a reference bus as well. So this is my reference bus which is supplying these P1 and P2. Now distribution generators are coming into picture. Okay, so this is my reference bus, and certain P1 was consumed, and some P2 was supplied. Okay, so this is basically when we are looking at, like, like a distributed like generation. Solar, let's assume, at our household, so it's like aggregated, and some P2 is present. So the power flows will be like, P1 and P2 in this particular. Like if I make a power balance equation, in this particular line, the power will be P1 minus P2. Okay, so if I use this particular philosophy, what I can do is I can write down the losses. So P losses are basically P1 plus minus P2 is square, and let's say R is equals to 1. So I will not consider that. So let's make a table P1 P2 and losses. So let's say P1 was 10 and P2 was 0. So in that case, total losses was 100. It is, sir, please conclude today's session in few words if possible for better understanding. Yes, so I will, yes, definitely I will conclude. And just let me, explain the cross subsidy. So let's say I keep P1 constant 10 and make it 1. Then it is 10 minus 1, 9. So the losses will be 81. If I make it 10 and 5, so the losses will be 25. If I make it 10 and 10, the losses will be 0. But what happens when generation is more in the distribution as compared to the consumption? So let's say 11, then it is 1 again. 10 minus 11 is 1, whole square is 1. And if it is 10 and 15, it is 25. 10 and 19, it is 81. And 10 and 20, it is same 100. So if you see initially, and if you apply the same allocation, proportional, let's say allocation to the P1 and allocation to the P2, you will get some values. So certain values will be like given as a allocation. So in this basically 100, 0, and let's assume I'm using the B1 beta 1 and beta 2 1 game theory based solution. So it will be like 100 plus 10, 110. Okay, and or I'm wrong. I think yes, it is basically P2 is negative this time. So this P2 is negative here. Okay, so if it is in opposite direction, we will consider P2 the same in the same formulation as a negative value. So P1 square is basically 100 plus beta 1, the coefficients will come exactly equals to 1. Okay, and if it is exactly equals to 1, then it will be 110 into minus 1. So it is minus 10, and that is equals to 90. But here, if I look at the value will be what? First 1, so it will be 1 square. Beta 1 is 1, and 10 minus 1, so it is minus 10, and that is equals to minus 9. So if you can see from here, the allocation to the first player has been reduced to some extent. Okay, but the DG at the generator is basically getting paid. So if let's say if we see that for losses, whatever is the allocation, somebody has to pay for those losses. So if a generator is there, and like for this particular case, the P1 is basically allocated 90 losses. So from the base case, like when nobody was there or no generation was there, it is still better off, and P2 was basically getting some money out of it. But if you look at the total summation, it is 81. So the total losses in the network is only 81, and still we are allocating 90 losses or 90 per unit losses to the player one. So this is what basically a cross subsidy in terms of loss allocation, that we are giving a benefit to the generator because it is helping in reduction the losses, and that cross subsidy, these are basically in like provided by cross subsidizing the P1. So that 9 will come from the allocation of P1. So if there are only 81 losses, nobody, it is quite common, like understood and easier, common sense that 90 should not be allocated. If 80 per unit is the total losses, 90 should not be allocated. So here we can say that we are doing a cross subsidy from player 1 to player 2. And like I have drawn this particular table. If you go beyond zero loss, then it will the picture will reverse, everything will be. So after here, like the some cross subsidy will be there, and after that part the picture will reverse. So I just like we are about to finish, so I will conclude my lecture. And I request you to solve it, this particular table as well. You will see how we are cross subsidizing from first player to the second player, and that is cross subsidy in terms of loss allocation, that when we have negative power flows. So for today's lecture, basically I'm not giving you that the game theory based methods are optimal. uh, this is basically, this entire presentation or the lecture was one of my work. And we identified or we looked upon some practices or some methods available, and we able to find out this gap, that okay, they are providing different allocation even though the actual system or the actual scenario remains same. So that's why we come up with a solution that okay, we should adopt game theory based solution. However, uh, it's all about like looking at the picture. So from the research point of view, I would say you can have different parameters to consider, and based upon that parameter, whichever contribution you can provide, like so far in this particular we have contributed that okay, uh, from the loss allocation point of view, there are different methods, and instead of using these methods, you should use game theory based method where both the beta 1 and beta 2 are 1. So it is easier for the calculation point of view, and it will not be unbiased, and the solution will not be unbiased. So fairness point of view we have considered. Okay. And from implementation point of view as well, that because of this aggregation or disaggregation, it will, the solution will not affect. But there are different methods, different assumptions you can go through, and you can come up with something else as well. So so far, yes, we have the network losses are also there. These losses has to be paid by someone. Okay. So here in this lecture, like basically we are trying to identify the methods by which we can allocate these losses to the different uh, parties. Okay. So we have like very basic minimalistic example we have considered, where the each line we are like basically, so instead of considering the entire network, we are considering the section of the network, which is like single line. And if you are able to identify the transactions, then there are different methods, and we finally concluded that game theory based method should be adopted instead of the other three, which is like proportionate, quadratic, and geometric allocation, because they give different answer uh, by virtual disaggregation at basically aggregation. So this is it. If you have any doubts so far in this particular lecture, please you can ask them. I can share one of my like conference paper. It is hardly 4 pages, and the entire lecture is from that paper only. So I have that with me as well. So that's why like all the numericals, the same numerical I have used there as well. So you can go through it. If you have any doubts, you can ask me. Yes, I will do. I will do it basically. It's one of my conference paper, hardly 4 pages, so you can go through it. and everything, whatever is in this paper I have explained to you. So Mohit, Yangya, do we, yes, do you have any questions? Please feel free to ask me. Okay, good. So there is two work for you. One is to basically, go through this cross subsidy part and see how what is the behavior, and then another is like how to use Shapley value. So I just calculated for player one only here, and then left for player two and three, and just this the very important part here is getting phi 2 equals to 0. So just it's food for your thought why we are getting Shapley value of second player equals to 0. So but I left it like I did not calculated it. I just left it for you, and if somebody is able to identify, please let me know, and I'm happy to discuss that as well. And yes, so just try to solve it, and you will get, if maybe I am wrong, maybe it is not equals to 0, so I just request you to solve it, and then we will yes, we can discuss it as well. So like why it is 0, what is the significance of it. Okay, so this is it. Thank you very much. Then the next section is 2 to 4. Okay, and that is like the first session is about risk management. So how the like we can do the risk management if there are uncertainties in the system, and then it is, I think, the price based economic dispatch will be discussed. So see you at 2 then. Thank you.